Hello, hello. I am going to work my way through the speeder problem in on worksheet 2, the second problem, where the cop is trying to catch the guy who's speeding in the car. I've drawn out a little diagram over here. So this is our billboard. Here's our road, our car that's speeding. So I'm going to use S as a subscript for the speeder, and our motorcycle cop, which I'm going to be using the subscript M to note all of this stuff. Now, the basic premise of this problem is pretty straightforward. Speeder's going by, he's driving at a constant speed, so his acceleration is 0. And the instant he passes the motorcycle cop and he sees that this guy is speeding, he starts accelerating to try to catch this guy. Now, in the first couple of seconds, the speeder is going to pull away from the cop. But since the officer is accelerating and the speeder is not, eventually his acceleration is going to reach the point where he's going to start catching up and closing that distance to catch up with the speeder. So at the end of this, up here, our speeder and our motorcycle cop are going to be at the same spot again. And so over the course of this distance, which we're going to call, I'm going to use D because of, you know what? I'm going to change this. I'm going to use C for car because S is just a bad example. So car, the speeder is in a car, so that they are going to cover the same distance and they're going to do it in the same amount of time. Because we are looking at the exact instant when the motorcycle cop actually catches the speeder, the guy in the car. Okay, so how long will it be before he overtakes the speeder? How far will the speeder travel? What will be the policeman's speed at that time? And then work, which you don't necessarily have to show me on this. These two we can find either at the same time or separately. This one, we have to find one of these before we can find this. So let's make our list of variables. Let's start with the motorcycle cop. We know his initial velocity is 0. We do not know his final velocity. That's one of the things we have to find. We know his acceleration. His acceleration is 4.00. Acceleration equals 4.00 meters per second squared. The distance traveled, we do not know. That's one of the things we're trying to find. And the time that has passed is one of the things we're trying to find. So these are the 3 things we want. There's a problem here, though. I just realized my head was totally in the way when I was drawing most of that. There's a problem here, though, in this information. We don't have enough information here to use our kinematic equations. We only have 2 knowns and 3 unknowns. We cannot use our kinematic equations unless we have 3 knowns, at least. So there's not enough information here for us to solve this problem. So let's look at the speeder, the car. The initial speed of the car is 30.0 meters per second. What's the final speed of the car, though? Well, because the acceleration of this car is 0, that means that the final velocity of the car is the same as the initial velocity. So we actually don't need either of these. What we need then is S, which we don't know, we're trying to find, and we need T, the time it takes for him to catch. Well, we don't really know that either. So we only have one known in this equation. But if we look at our third kinematic equation, and we set it up twice, once for the speeder and once for the motorcycle. I'm going to try and do that. Well, I'll write the equation here. So S equals VI T plus AT squared over 2. We know that S and T have to be the same for both of them because they're going to travel the same distance and they're going to do it in the same amount of time. So S and T, we don't need any extra subscripts on. They are just the same. So if we write this equation out for the motorcycle cop, his initial velocity is 0, so we don't need this part. All we need is S equals AT squared over 2. So for the cop, S is going to be equal to the acceleration of the motorcycle times the time that passes divided by 2. We don't know T and we don't know S. But if we do the same equation here for the car, for the speeder, acceleration is 0. And so it's just the first part of the equation. So the distance traveled by the speeder is equal to his velocity, his initial velocity, which is just his velocity, right? He doesn't have an initial and a final. It's the same value. It doesn't change. So the velocity of the car times the time that passes. Well, we have... Let's switch colors. We don't know this, but it's the same as this. Purple marker's missing. Wait, I just picked up another green marker. Hang on. There it is. We don't know this, but it's the same as this. So both of these T's have to be the same, and both of these S's have to be the same. So if we are looking for time, which is what A is asking us for, what we can do is we can set these two equations equal to each other. So the acceleration of the motorcycle times the time squared over 2, which is equal to S, but S is also equal to the velocity of the car, or the speeder, times the time it takes. Well, if we drop this S out, this becomes the acceleration of the motorcycle times the time squared over 2 is equal to the velocity of the car times the time that passes. Well, we can divide both sides by t. We divide this by t, it's going to cancel. And t squared divided by t is going to cancel out the squared. So the acceleration of the motorcycle times time over 2 is equal to the velocity of the car. With this equation, we only have one unknown. The only thing we don't know in this equation is t. So we can solve this for t by multiplying by 2 and dividing by the acceleration of the motorcycle. So t is equal to 2 times the velocity of the car divided by the acceleration of the motorcycle. So if I move over here now, t is going to be equal to 2 times the velocity of the car, which is 30 meters per second, 30.0. Remember, this is an integer because it came from our source equation, divided by the acceleration of the motorcycle, which is 4.00 meters per second squared, meters per second squared. So 2 times 30 is 60, divided by 4 is 15. So we get 15. We have 3 sig-figs here, 3 sig-figs here, and an infinite number of sig-figs here. So between infinity, 3, and 3, we should have 3 sig-figs in our answer. We only have 2. So to keep the number of sig-figs we're going to add 0.0 to the end of that, which is what happened with these numbers here that have all the zeros at the end. So 15 seconds is going to be our time. So this is the answer here, 15.0 seconds. How far will the speeder travel before being overtaken? Well, we can come back. I'm going to switch colors here. To one of these two equations, and either one will work. Now that we know t, we can plug in 15 seconds to either of these equations to calculate s. Now, I'm going to use this equation because it's simpler than this one is. So I'm going to use this equation. S is equal to VC, which is 30, times the time that has passed, which we determined to be 15 seconds. 15 times 3 is 45, so 450 meters. So this would be the answer here. What would be the policeman's speed at the instant when the speeder is overtaken? For that, we would go back to kinematics equation 1. So I'll switch colors here again to green. Kinematics equation 1, and we would be doing it for the motorcycle. You know what? Let me pull my stool up and write this up there instead, since we're dealing with the motorcycle and not the speeder. So the final velocity of... Ooh, can you see that? No, you can't see that. How about this one? Can you see this? Yes. Okay, super. Okay, so the final velocity of the motorcycle is equal to the initial velocity of the motorcycle plus the acceleration of the motorcycle times the time that it took. We know the initial velocity is 0. We know that the acceleration is 4, and we know we now know that t, I'm standing in front of it, is 15 right here. So 15 times 4, the final velocity is going to be, well, I'll write this out. So that's an S. VF equals 4.00 times 15.0. So that is going to be 60 meters per second. So C would be 60.0 meters per second. And that's how you'd solve that. The key here, a lot of times when you have a problem like this, your key is going to be this equation. Okay, this equation can be set up, especially when one of your initial velocities is 0 and the other one is not. This equation will make your calculations significantly easier. Okay, so that's how you would solve this problem. I'm going to end this video here, and I will make a third video, which will talk about how to start the arrow problem. I don't think I'm going to actually finish the arrow problem, but I am going to show you how to start it. And then that's going to be your homework, because I want you to try to finish it based on this information and on what I give you in my next video. So, hope this helped.